Hey guys, this is topic 4. Definitely the most difficult topic of the year for most people. It's motions of the Earth, Moon, and Sun. And just to let you know, the difficulty lies in this is basically picturing things, how they move from the Earth's perspective. So, how does the sun move across our sky? How does the moon move across our sky? And these are all questions we're going to be answering in the next few slides, if you don't already know. So just questions to think about if you want to try them before you even hear the answers in a moment. In what way do stars, planets, and the moon and the sun move across our sky? What causes these motions to occur? And what do you think is meant by apparent motion and real motion? All right, which are two very different things. So here are the answers one by one, just to kind of go through it. Number one, you probably already know. Sunrise in the east, sets in the west. Right? You've probably known that since elementary school, I'm sure. Is it exactly east and west? This time of year, springtime, yes. But as we get towards the summertime, it's going to start shifting, and same thing during the winter. So we'll talk about those patterns. Moon rises in the east, sets in the west also. So what do you think the stars do? Guess what? They do the same. They rise in the east, set in the west. But not all stars, because you guys already know of one star that stays in place, and that is Polaris. All right, you learned that way back, topic 2. And most objects rise in the east, set in the west. And the reason why, we'll get to that in a moment. So the star we already know that does not rise or set, that's going to be Polaris, located over the North Pole always, over the spin axis. So it stays in our sky always. Okay, we just can't see it during the day because the sunlight blocks it out. Okay, so we'll talk more about that in a little bit. Do you think it's the objects moving? Nope. It's actually us doing the moving on Earth. The Earth spins. It takes 24 hours to spin once. It's actually 23 hours, 56 minutes, and 4 seconds exactly. But we round it up to 24 hours. Motions are actually caused by the Earth rotating. So things moving across our sky on a daily basis, that's because of the Earth's rotation. All right, sun rising and setting, moon rising and setting, stars also doing the same. So it's all about Earth's motion of rotation. Now don't mix that up with revolution. All right, we're going to go over those two motions in a little bit. Okay, apparent motion versus real motion. All right, now this is kind of confusing, but apparent is how something appears to move across our sky. All right, so it's as we see it from the Earth. Okay, back in topic 3, we learned about real motions, right? Because we had planets revolving around the sun. Okay, and the revolution is actually a real motion. It's something that it's doing out in the universe. All right, we only see apparent motions because of our motion that we're going through here on Earth, which is rotation or revolution. Okay, so the apparent motion of celestial objects is caused by the Earth's rotation. And hard to tell real motions of stars because they're so far away from us, right? We don't see them move much year to year. Those constellations, if we come back millions of years from now, yes, they will be in different spots. Okay, but now they are where they are. Every year we see the constellations in the same place. All right, circumpolar stars. All right, these are stars that are always in our sky, like Polaris. They never rise or set. And they appear to revolve around Polaris. And I'm going to say in quotes, revolve. They're not really revolving around Polaris. We're rotating. So I remind you that. Polaris is always found directly over the North Pole, and these will make a circular path throughout the evening around Polaris. So the picture you're seeing, this is called a star trail. And basically we set up a camera on a tripod, and camera shutters open and shut to take a picture, to collect what they see. This camera is set on a special setting where it's set to open the shutter, leave it open, and continuously collect light for hours at times. And the stars move across the sky at 15 degrees per hour, so this is a time exposure picture. And if each were arcs of about 60 degrees, you would take 60 divided by 15 degrees per hour, and you would get that the picture was 4 hours of exposure time. So that's the sort of question you can get on the regions. So you just take the amount of degrees that the star moved, divide it by 15 degrees per hour, and that will give you how many hours this picture is representing. All right, so here's just a quick little animation to kind of show you that I've gotten from a teacher from upstate. But basically, this is the Little Dipper, and Polaris is in the center right here. Polaris just moves a little bit in the sky, barely though, but it stays right over that area in the North Pole. So it pretty much stays put. The other stars make a circular path. This shows it resetting, but obviously that would be the next evening when I came out again. All right. All right, next, I want to talk about the motions of the planets. Planets are definitely a little bit of a difficult thing to actually figure out. And scientists years ago, they had a hard time with this. All right, so when we are out in space, okay, the real motion of the planets, obviously the ones that are closer to the sun move faster, the ones that are further from the sun move slower. So to us, an observer on Earth, which we're the third planet out, okay, we see the other planets sometimes coming towards us or moving away from us. And as a result, in our sky, it's not going to be a straight line pattern. It's going to tend to change direction. All right, so I'm going to talk about that change of direction. So planetary motions move across the sky in a complicated pattern. And the complicated motion is caused by the planets revolving in different orbits at different speeds. So as a result, the planets will make loops in our sky. All right, they'll tend to actually exhibit retrograde motion occasionally, which is a backwards motion in the sky. So it will start forward, and then it will actually loop backwards. So I'll show you an animation of that with Mars in a moment. Okay, so let me load this up. And here is Mars coming across the sky with the backdrop of the other constellations. And you'll see it kind of makes a U-turn basically. And then it makes another U-turn and then goes straight again. Okay, so this loop pattern, so if you see it in a question, that means that it is a planet that is making that type of motion. So that's something we look for. So if you see that complicated pattern, the planet is the only thing that can do that, because we see a combination of its real motion and its apparent motion. Because we're moving, the planet's moving, so across our sky we see that complicated motion as a result. All right, the moon, again, rises in the east, sets in the west, but there is a pattern with it day to day. It rises and sets 50 minutes later each day. So we actually have moonrise, moonset in the paper each day or online that you can actually look up. It will also shift eastward each night you come out at the same time. So if you came out at 6 p.m. one night, saw it in a certain location in the sky, the next night you come out, it will be eastward of its location at that same 6 o'clock time. All right. The next thing I'm gonna show you on a under the camera, because we have to draw some stuff on it. All right, so this is basically an Earth and time diagram, which we can actually figure out the clock times on this diagram very easily just by looking at the light rays and the orientation of the Earth. Okay, we're looking at the North Pole in the center in this diagram. Okay, the first thing we're gonna do, we're gonna draw a line down this, and we're going to shade in the side that is nighttime. So that is night, and this is daytime. Okay, and we rotate, as you guessed it, either west to east, whee, or counterclockwise. Okay, so we're rotating in that way. All right, and the sun rays are lighting up half the Earth, half the other side. The other side is actually nighttime. Okay, directly in the middle of the sun light, which right here, that's going to be 12 noon, which is also known as 12 p.m. So make sure you don't mix up AM, PM. Okay, over on this side, opposite that, is going to be 12 AM or midnight. Now you ask, what's the time here and here? That will happen. That will come up in questions. Okay, we're rotating this way. We're going from light to dark as we rotate. So this one is 6 p.m., also known as sunset. And this is 6 a.m. sunrise because you're going dark to light as we rotate. Okay, now you ask, well, sometimes the sun doesn't rise at 6 a.m., 6 p.m. All right, well, they decided to use equinox date, which divides up the hours exactly, 12 hours daylight, 12 hours darkness, just for simplicity in the diagram. All right, obviously, if we had more daylight hours in the northern hemisphere, this diagram would change slightly, but we're just going to take it on average as that. Okay, you can also estimate in between times. So if this is 12 p.m., this is 6 p.m., this could also be 3 p.m. All right, you could do that throughout the whole diagram to get times. Now, this is a top view of the Earth, North Pole. If I flip it over, I have my other one. Sorry, I wrote dark ink, so you can't see. You can see the writing from the other side. But this is a side view of the Earth, North Pole on top, South Pole on the bottom. So this is kind of like a side view of the Earth. Okay, so if I do the same thing, shade in nighttime and daytime. Now, we're rotating counterclockwise, so around the North Pole, it looks like that. Or you can go with the west to east orientation, like we talked about. Whee! Okay, so we're rotating like this. This is still 12 noon. This is still 12 a.m. Now, this whole line here is a line of longitude, so this is all the same time zone. Okay, from the North Pole to the South Pole. This is rotating from light to dark, so this is going to be 6 p.m. all the way up and down this line. It doesn't matter if I'm here or here. This is all 6 p.m. And you ask, where is 6 a.m.? It's on the other side of the globe, out of your view. So this is the complication of this. So looking from a side view versus a top view. Okay, so before you were looking, you had 6 a.m., 6 p.m. Now we turned it, so now we're only looking at this side of the Earth. So when you see it on this side, you're looking at this side of the Earth. 6 a.m. is on the other side where we can't see it. Okay, so that's a little complicated for some students, but that's the way it, you have to interpret those diagrams. Okay. Whoops. Get back to my PowerPoint. Apologize for the little delay here. Okay. Also, I want to talk about evidence of rotation and revolution. Okay. So Foucault pendulum. Okay, this is a freely swinging pendulum that is attached to the ceiling. It changes angle by 15 degrees each hour. Okay, and it swings back and forth, and museums will have these set up, and they'll sometimes knock down dominoes around the outside edge of the circle. Okay, so each hour you come back, you'll see another domino knocked down. So they have it timed out that way. Why does it change direction? It's not because the pendulum's changing direction, it's us rotating beneath the pendulum. All right, so that's evidence of the Earth's rotation. Okay, so suspended from the ceiling, it goes back and forth, and that's how we get our, because of the Earth's rotation. Okay, also one more thing about rotation before we get on to our next evidence is that the velocity of rotation. Okay, if you look at the area around the equator, that's a larger circle than if you were circling around the North or South Pole areas, okay, when you're spinning the globe. Okay, so the Earth is actually spinning faster in a circle at the equator than it is at the poles. As a result, things that are traveling large distances over the Earth's surface are going to deflect path naturally. All right, and we call this idea Coriolis effect. So Coriolis effect is the deflection of matter at the Earth's surface due to the Earth's rotation. In the northern hemisphere, it's going to be a deflection to the right. In the southern hemisphere, it is going to be a deflection of the left. Now, the only thing that you have to be careful of is make sure you're pretending you're the arrow or the thing facing the direction. It's always going to be your perspective, which way you're facing. That's the direction right or left of. So northern hemisphere to the right, southern hemisphere to the left. Okay, so here's an example of what I was just talking about. So North Pole is here. So the weather balloon that's trying to travel towards the equator gets deflected to the right of its perspective. So this is actually to the right of it in the northern hemisphere. So a little tricky. Okay, I'm going to show you a couple of animations of this also. Okay, the first one is I'm going to show you is going to be in the northern hemisphere. So it's a plane starting up in Alaska and is traveling to Florida, but it didn't pay attention to Coriolis and it ended up in Mexico. So again, because the Earth's rotating beneath it, it will tend to deflect path naturally because of Coriolis effect. Right? This only works for things traveling large distances. Okay, another example, southern hemisphere. Remember, it deflects to the left. So we're going to start in Argentina. We're going to try to head to Brazil for the Olympic Games. All right, and we're going to end up in the Amazon jungle because we deflected to the left because we ignored Coriolis once again. Okay, now that's rotation. So rotation, the two evidences, Foucault pendulum and Coriolis effect. Okay, now revolution on the other hand, which remember is the orbit around the sun. A couple things change. Okay, number one is the constellations that we see in our sky. You guys know them as the zodiac symbols sometimes. All right, so zodiac symbols are an example of groupings of constellations. As the Earth revolves around the sun, we see different stars as the Earth changes position in its orbit. So during December, right, it's actually end of November into December, you'll see Sagittarius in the sky. End of June into July, you'll see Cancer constellation in the sky. Right, and the reason why? We are orbiting the sun. So you see in the diagram here, the Earth orbits the sun counterclockwise. So just like it spins counterclockwise, it also revolves that way. And each position, you'll see different sets of constellations. So in this position here, you'll see Leo, Virgo, and Libra. Okay, this position, if you're a little further, you'll see Scorpio come into view, and then Sagittarius, then Capricorn. So what it does, each position, it will see a different constellation due to the revolution. And also, if you're a sky watcher, if you want to actually find these constellations, you can use pointer stars like these here, which will actually point to certain stars in a constellation. But luckily, you guys have apps now that do this. So you could actually get an app, a star finder app, which you could, point at the sky and find any constellation anytime. It's really cool. Okay, also evidence of revolution, we have changing seasons. So southern hemisphere will point towards or away from the sun, causing seasonal changes. And remember, the Earth's orbit around the sun is an ellipse. And as a result, June, July, the Earth is furthest away from the sun. So opposite of what we would think. All right, the seasons, remember, summertime, we're actually further away from the sun. It has nothing to do with distance, our season. So the sun will appear smaller in our sky in June, July because we're further away. And in December, January, the Earth is closer to the sun, so therefore it will appear slightly larger in our sky. Okay, and the same thing happens with the moon sometimes in its orbit. All right, we see this. They call them supermoons occasionally, and that's caused by the moon being closer or further away. You get supermoons or smaller moons, actually, in some cases. All right, the next part is basically a way of looking at the sky. So we have to first talk about a compass. All right, and a compass gives you an azimuth or a bearing, which is a direction on the horizon. Okay, so if you're a boater, you know about these types of compasses down here on the bottom right. Okay, well, this is how they work. So north is 0 degrees. Okay, in between would be northeast, obviously, and then you have east at 90 degrees. South is 180, west is 270. All right, and the compass goes from 0 to 359 degrees, and then when you get back to 0 again, then you're back at north. So this tells your direction along the horizon, and we're going to use that in the next piece of information that we're going to be talking about. All right, and they have these plastic hemisphere things. This is like a big planetarium over your head, and in this diagram, they have east in the foreground, south on the left side, north on the right, and west in the backdrop. Okay, zenith is a point above my head that's 90 degrees above my head from the horizon. So we measure angles from 0 to 90 on these diagrams. Okay, so the first example, that's the person looking up at the sky. 90 degrees above their head is called zenith. And if we plot a star in the north sky, right here, this is 80 degrees in the north sky. Okay, this star over here is approximately 80 degrees in the south sky, right? Because again, north is this way, south was this way, west is in the backdrop. So I'm going to show you an example of that in a moment, how we're to plot a backdrop star. Okay, so the last example, same idea, but we put a star in the west sky, which is in the backdrop at 45 degrees. Remember, 90 is all the way up here, 45 is halfway between 0 and 90. And lastly, just one more example, a star at 20 degrees in the northern sky. So it's a little lower, you can see. So you can kind of think of this like a big protractor to figure out angles. Okay, I thank you guys for tuning in, and hopefully all these things are sinking in. But again, ask questions anytime, send me emails. All right, thanks for listening and watching, guys.